As you know, we live in an ocean of air, the atmosphere. This transparent part of our environment reveals itself when it starts to move, shaking the trees and blowing snow. We live in the lowest portion of the Earth's atmosphere, a layer called the troposphere. Most of the phenomena we call weather occurs in this layer. Air, of course, plays an essential role in life on Earth. The chemistry of air is fully integrated into the chemistry of life. Carbon dioxide and oxygen flow from plant to animal and back again, packaging and releasing energy from the sun. Air mediates this process. The significant knowledge we have today about the physics and chemistry of our atmosphere comes from the research and experimentation of a number of great minds, including the 18th century work of Scheele and Priestley, discoverers of oxygen. Others followed. They discovered the essential role oxygen plays in sustaining life. Air is complex. Scientists have determined that oxygen makes up approximately 21% of air, nitrogen 78%, and a number of other gases make up the remaining 1%. Carbon dioxide comes in at 0.04%. It is a testament to human ingenuity that we have found ways to determine the components of air. Let's look at a method for determining the percent of oxygen in air. This process relies on the fact that oxygen is highly reactive. Observe a fire and you are witnessing oxidation. Oxygen is reacting primarily with carbon in the wood in such a way that energy is being released at a fast rate. Carbon dioxide is one of the products of this process. Fire is an example of rapid oxidation. Oxidation can also be a slow process. Over a period of time, oxygen will combine with iron, producing rust. The reddish color on this metal roof is rust. Rust is a form of iron oxide, oxygen combined with iron. We're going to use the chemistry of rust to estimate the percent of oxygen in air. We need some steel wool. It contains iron. Also a plastic test tube or similar tube closed at one end, and a container of water. The process is simple, as this animation demonstrates. Secure a small piece of damp steel wool in the bottom of the test tube. Rotate the tube and suspend it with the open end submerged in a container of water. Oxygen will start to react with the iron in the steel wool, forming iron oxide. This removes the oxygen from the air in the tube. The missing oxygen is replaced by water, being pushed up into the tube by air pressure. When the process is finished, the added volume of water in the tube equals the volume of removed oxygen. Let's set up some equipment so we can actually measure the volume of oxygen in air. There are a number of ways to do this. This is the method I used. These plastic tubes are calibrated in milliliters. I drilled a hole at the 10 milliliter mark. This will be the starting volume of air, as water will enter the tube to this point. A hole in the cap allows water in at the base. To increase the rate of oxidation, dampen the steel wool with dilute acetic acid, common vinegar. I used 5% acetic acid, diluted 50% with water. Remove excess liquid from the steel wool and push it into the bottom of the tube. The wide cap allows us to invert the tube and stand it in a container of water, eliminating the need to use a test tube holder. I had to add some weight to the bottom of the tubes. They tended to fall over without it. I set up two tubes, one with steel wool, one without, a control, just to make sure that temperature fluctuations or some other effect wasn't influencing our results. With the tubes in place and the water levels at the 10 milliliter mark, I set up a video camera to record the event. The process is very slow. This time lapse covers 1 hour. In this period, the water moved up 1.5 milliliters on the scale. As the oxygen depletes, the process slows even more. I set the equipment up again, and this time let it run overnight, about 8 hours. The next morning, the water level had settled at the 8 milliliter mark. The water level in the control is unchanged, confirming results. Of the original 10 milliliters of air in the tube, 2 milliliters had been replaced by water. This water represents the volume of oxygen that had been removed from the air, 2 milliliters. According to our results, oxygen makes up 2/10 or 20% of Earth's air, a good approximation. The color change tells us that the steel wool has rusted. This sample is fully rusted, flakes of rust falling from the steel wool. With this simple method, we have estimated that air is 20% oxygen, close to the accepted value of 21%. Some changes that would improve this procedure include using a taller, thinner tube. This would give better resolution of the scale, improving measurements. And we ignored the effect the steel wool had on the actual volume of air in the tube. Allowing for this would improve results. View our video on oxygen for a demonstration on how to collect and test oxygen produced by photosynthesis. And for more science and technology videos and projects, visit our website, hyloroad.com.